Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. This is video 8 of the series on linear relations, and we'll be talking about how to solve linear inequalities, which happens to be the simplest type of inequality. Inequalities in general are quite difficult to solve. If we look at the screen here, before we embark on solving linear inequalities that I abbreviate to LIEs, linear inequalities, I think it's important to discuss some notation regarding inequalities because many students get very confused with the various symbols that are used to denote inequalities. So let's look at the first. This is an inequality. We have a variable on the left, a constant on the right. So a will always denote a constant, and x will denote the variable which is allowed to change. So this reads x less than a. So it would be x less than a. In short, less than a. What this means is that we have something that is to the left and it's exclusive. So we can call it left exclusive. Okay, that means all the values to the left of a excluding a. So less than a means excluding a. So it's left exclusive. To exclude something means to put a circle at that point on the number line. The O means a hole. So when you're excluding a point on the number line, you put a hole on top of that point. So left exclusive, we use a hole. The next inequality, x less than or equal to a. You pronounce that x less than or equal to a. That's a left inclusive, because we're to the left of a and we're including a. When we include a, we use a solid dot on the number line. So that's to the left and including a. To the left and including a. So these are the left inequalities. Let's look at the right inequalities. X greater than a. You pronounce it x greater than a. And that's a right exclusive inequality. That means all numbers to the right of a are good, excluding a. Of course, exclusive means you have a hole on top of a on the number line. So right exclusive, you're moving to the right, excluding a. Okay? X greater than or equal to a. You pronounce x greater than or equal to a. And that would be a right inclusive. So you're moving to the right of a and you're including a. So we use a solid dot to represent inclusive. Okay, and these are all the right inequalities. So to recap, we use an open circle to represent exclusivity, and we use a solid dot to represent inclusivity. To exclude means to leave out. To include means to leave in. So these are the left exclusive and left inclusive. This is the right exclusive, right inclusive. So we can move on to the next slide. Now we'll be talking about between inequalities. In this example over here, we have x, the variable, is somewhere between a and b. We pronounce greater than a and less than b. X is greater than a and less than b. Notice the wording. x, you always start off at the center. X is greater than a, and x is less than b. Okay? Notice that it's exclusive at the endpoints. In other words, greater than a means excluding a. Less than b means excluding b. So these are all x values between a and b, excluding a and excluding b. And we use open circles on top of a and b. So between means you have a double arrow like so. And now we go on to another inequality, x greater than or equal to a, and x is less than or equal to b. That's the way you pronounce that. Always start off at the center. X greater than or equal to a, and x is less than or equal to b. So that's also a between inequality, and you pronounce it greater than or equal to a, and less than or equal to b. So that's between, so we use a double arrow like so, and it's inclusive. The equal sign means including a. The equal sign means including b. So it's an inclusive inequality at both endpoints, whereas this is an exclusive inequality at both endpoints. We have a hole on the left, hole on the right. We have a solid dot on the left, solid dot on the right. And next, we go to the next inequality here. You pronounce this x greater than a and x less than or equal to b. So that's x greater than a and x less than or equal to b. And again, it's down here, greater than a and less than or equal to b. So it's definitely a between inequality, but it's left exclusive and right inclusive. Left exclusive, that means a is excluded and b is included. And finally, x greater than or equal to a and x less than b. So x greater than or equal to a and x less than b. Greater than or equal to a and less than b. So it's certainly a between inequality, but it's left inclusive and right exclusive. Left inclusive because of the equal sign, and right inclusive because there's no equal sign. So these are all between inequalities. I would urge you to go over them, and we'll proceed on to the next slide to solve some simple linear inequalities. Let's look at the first question, Q2. It says solve and graph the solution of the linear inequality over R and Z. R represents the set of real numbers, and Z represents the set of integers. So they want a solution over the real numbers and then over the integers. So let's have a look at the inequality. When you stand back, you try to locate. The first thing you try to do is locate the inequality symbol. There it is right there. It says greater than. Okay. The next thing you do is scan the whole inequality and look for the, notice the first thing I notice is that there's only one variable, x. This could be more than one variable. It could have two or more variables. But we'll discuss those types of inequalities. They're obviously more difficult. We'll discuss those types of inequalities in future videos. But for now, we'll be dealing with inequalities in a single variable. So we've only got one variable. And another thing I notice is that all the x's appear to the power 1. To the power 1. So that's what constitutes a linear inequality. If any of the x's appeared to a higher power, like power 2 or power 3, or to a negative power, like -1, -2, etc., it would certainly not be a linear inequality. So we have a simple linear inequality on our hands. Okay, the first thing you want to do is expand to remove all the brackets. Do not move anything, just expand. So when we expand, we have a bullet and two targets. It expands as -3x plus 3. The 3 gets dropped down. The inequality symbol remains. And the 4 gets dropped down. And we expand the minus sign inside the brackets. We get -2x minus 5. And at this point, we can use backward bin gathering, BBG, in order to collect all the x's on the left and all the constants on the right. So on the left, we can open up an x bin. We'll scan the expression, pick up a -3, drop it inside the bin. On the right, we pick up -2. When you move it over, it becomes +2 and close up the bin. We're done with the x term. Then we go over to the right-hand side and we open up a constant bin. We scan the left-hand side for constants. We see a 3 becomes -3 because we're moving it over. 3 becomes -3 because we're moving it over. And 4 is a drop down, and -5 is a drop down, and you can close up the bin. The next thing to do is to simplify inside each bin. -3 plus 2 is -1. Drop it inside the bin. And then -3 plus 4 minus 5 is -7. Drop it inside the bin. And at the end is the crucial part. Okay, to solve for x over here, we have to divide both sides by -1. Whenever you divide both sides of an inequality by a negative number, you have to change the direction of the inequality symbol. CD means change direction. Why? Because we're dividing by a negative number. Okay? If we were dividing by a positive number, we maintain the sign of the same direction for the inequality. But when you divide by a negative number, the sense of the inequality changes direction. So we have to do a CD over here because CD stands for change direction because we're dividing by a negative number. So when you divide both sides by -1, you get x on the left. You change the sense of the inequality, or you change the direction of the inequality. And of course, when you divide -7 by -1, you get 7. So at the end, we get x less than 7. Because less than has no equal sign, okay, the 7 has an open circle. In other words, the solution set excludes the number 7. Okay, so now we find a solution over the real numbers and then over the integers. X less than 7, all we do is rewrite it as x less than 7. Okay, and x less than 7 over the real numbers is just a horizontal line on the number line. And here we go. So horizontal line on the number line over the real numbers. Of course, at 7, here's the number line down here. There's the origin for the number line. And we have a hole on top of the 7 because the 7 has been excluded. And we draw a line pointing to the left, and the arrow means that all negative numbers are included in the solution set. And now let's solve the same inequality over the set of integers. Okay, x less than 7 over the set of integers means 6, 5, 4, 3, 2, 1, all the way down to -infinity. So again, the 7 is excluded. So the solution set are just these solid dots. So the solution set over the set of integers is a discrete set. It's infinite, but it's discrete only at the integers. 6, 5, 4, 3, 2, 1, 0, -1, -2, -3, etc. But over the real numbers, the line is a solid line because all the real numbers are included. All the numbers between 7 and 6 are included, excluding 7. All the numbers between 6 and 5 are included. Every possible real number needs to be included, and that's why we draw a solid line to the left. And so graphically, we have a discrete set over here over the set of integers and a solid line over the set of real numbers. We have exclusive there, and we're done. Let's go on to the next slide. Q3 involves the same ideas as Q2, the one we just finished looking at. And again, it says solve and graph the solution of the linear inequality over the real numbers and then over the integers, over both sets. And again, LIE stands for linear inequality. And sometimes we call the solution the solution set. Okay, so let's have a look at the inequality. The first thing I do is locate the inequality symbol. That says less than or equal to. So it's an inclusive inequality. The last one we did was an exclusive inequality. It had no equal sign. This one doesn't have an equal sign. Therefore, whatever we get, it has to include the endpoint. The first thing you want to do, first of all, you notice it's linear, okay? X appears to the power 1, power 1, power 1, so it's definitely linear. The first thing you want to do is expand to remove all the brackets. Over here we have a bullet and two targets. When we expand, we get a 6.x minus 3. Minus 5x is a drop down, 1 is a drop down. Then we hit the inequality, and 5 is a drop down. And we distribute the minus sign inside the brackets. We get minus 2x plus 3. And then 7x is just a drop down. And now we're going to use backward bin gathering to rapidly gather up like terms. We open up an X bin on the left-hand side. We scan the left-hand side of the inequality first. We pick up a 6. We pick up negative 5. And then on the right-hand side, we pick up negative 2. Moving it over becomes positive 2. And then positive 7, moving it over becomes negative 7. And you close up the bin because we've exhausted all the X terms. Then you hit the inequality, and then we're going to open up a constant bin. We scan the left-hand side first. Negative 3 moves over to give us positive 3. Drop it inside the bin. 1 moves over to give us negative 1. And then 5 is just a drop down. 3 is just a drop down. Again, we simplify inside each bin. 6 minus 5 is 1, plus 2 is 3. Minus 7 is minus 4. Drop it inside the bin. And over here, we've got 3 plus 8 is 11 good guys and 1 bad guy. So we've got 10. Notice we have not touched the inequality at all. At this stage, to solve for x, we notice that we have to divide by negative 4. When you divide by a negative number, you must change the direction of the inequality. And so that's what we do. Negative 4 divided by negative 4 will just give you 1. So there's the x. We have to change the direction of the inequality. So less than or equal to becomes greater than or equal to. And then 10 divided by negative 4 will give us minus 5 over 2. The equal sign means that the endpoint over here is included. So the equal sign means that the endpoint minus 5 over 2 is included. And so now we find the real solution and the integer solution to our linear inequality. For the real solution, all you do is grab this guy and copy paste. And that denotes a line. It denotes a solid line where the endpoint has a solid dot. Why does it denote a line? Because it's over the real numbers. Over the integers, x greater than or equal to negative 5 over 2 means that we have to start off at negative 2. Okay, and we proceed to the right. So negative 2, negative 1, 0, 1, 2, 3, etc. Because negative 2 is the first integer to the right of minus 5 over 2. And now we'll look at the graphs over here. Over the real numbers, we said that x has to be greater than minus 5 over 2, which is minus 2.5. So you go to minus 2.5 on the number line, put a big solid dot there. Again, the solid dot means that we included the endpoint because of the equal sign. So we put a solid dot there, and then all the real numbers to the right will be included in the solution set over the real numbers. Now we turn our attention to the integer solution. Well, for the real numbers, we could start at negative 2.5. But for the integers, we need to start at negative 2 because negative 2.5 is not an integer. So we start off at negative 2 and go through all the integers to the right of negative 2. So we proceed dot, 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 etc., all the way to positive infinity over the integers. Whereas for the reals, we started off at negative 2.5 inclusive and proceeded over to the right over all possible real numbers. And that's why it's a solid line. Question 5 will be the final question we'll do for the time being on solving linear inequalities in one variable. And again, it says solve and graph the solution of the linear inequality over the real numbers and then over the set of integers. So if you take a bird's eye view of the inequality here, locate the inequality symbol first. There it is. So always be aware of where that inequality symbol is at all times. The first order of business is to expand. What we want to do is remove all the brackets just like we did before. So we have a bullet and 2 targets. We're going to expand there. We have a bullet and 2 targets. We're going to expand there. So 2x is a drop down. When we expand here, we get a minus 3 plus 12x. 4 is a drop down. Then we hit the inequality, just drop it down. 6 is a drop down. And now we have to expand. We get a 2 dot 1, which is 2. And 2 dot negative 2x, which is minus 4x. And 5x is just a drop down. And now we've removed all the brackets. It's time to backward bin gather to collect like terms. We open up an X bin on the left-hand side, and we scan for X terms. From left to right, we pick up a 2, drop it inside the bin. We pick up 12, drop it inside the bin. Now we move over to the right-hand side. We pick up negative 4, becomes positive 4, and then 5 becomes negative 5. And you can close up the X bin. Then we hit the inequality again. Now we open up a constant bin, scan from left to right. We pick up negative 3, becomes positive 3 because we're moving it over. And 4 becomes negative 4. And 6 is just a drop down. And 2 is just a drop down. And you close up the bin. Now we'll simplify inside each bin. We have 2 plus 12 is 14, plus 4 is 18 good guys and 5 bad guys. So we get 13, drop it inside the bin. And then we get 3 plus 6 is 9, plus 2 is 11 good guys and 4 bad guys. So 11 minus 4 is 7, drop it inside the bin. And now we have to divide both sides by 13. And you'll notice that 13 is a positive number. When you divide both sides by a positive number at the end of the problem, there is no change in direction for the inequality. So the inequality maintains its original direction because we're dividing by a positive number. Okay? So when we divide both sides by 13, we get x on the left. On the right, we get 7 over 13. Now, 7 over 13 is roughly 1/2, which is roughly about 0.5. And again, the equal sign here indicates that the endpoint, 7 over 13, is included. Okay, so we use a solid dot for inclusion. Now let's look at the real solution. Of course, for the real solution, you just grab this and drop it down. And of course, it describes a real line. And I mean a solid line. And the endpoint 7 over 13 is included in that solid line. And x less than or equal to 7 over 13 means all real numbers less than or equal to 7 over 13 or to the left of 7 over 13. Okay, then over the integers, the first integer we encounter, which is less than 7 over 13, is 0. So all the integers to the left of 0 are included in the solution set over the integers. And of course, these represent dots. And because there's an equal sign here, we're going to use solid dots right through. Okay, so all we need to do over here is to graph this on the real number line. So we have a number line here, and this will represent our solution over the real numbers, and this will represent our solution over the integers. So over the real numbers, all we have to do is locate 7 over 13, which is roughly about 0.5. There it is there. You put a solid dot there, and then all the real numbers to the left of that boundary are in the solution set over the real numbers. Of course, 7 over 13 is not an integer, but the next integer to the left of it is 0. So we put a solid dot at 0 and then include -1, -2, -3, all the way down to -infinity. And the same thing over the reals. It goes all the way down to -infinity. And so this is the graph over the integers and over the reals for that linear inequality that we started with up here. Okay, we're going to do an over and out. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MathLab Tutorials in Toronto.